Assalamu alaikum, students and friends. Today's episode focuses on colligative properties of solutions such as the boiling point elevation, the freezing point depression, and osmotic pressure. So just stick around, watch, and learn. Colligative properties of solutions depend on the solute to solvent ratio. In other words, these properties depend on the amount of the solute, but not on the identity of the solute in a given solvent. We say that the greater the concentration of solute in the solution, the greater is the boiling point elevation. And the first colligative property we shall talk about is the boiling point elevation, denoted here by delta T sub B. It describes the phenomenon that the boiling point of a liquid will be higher when another compound is added, meaning that a solution has a higher boiling point than a pure solvent. This happens whenever a non-volatile solute, such as a salt, is added to a pure solvent such as water. For example, we want to calculate the boiling point of a 2.5% solution. All right, this is percentage by mass of sodium chloride in water. So, we identify the mass of the solute or sodium chloride equal to 2.5 grams. And then the mass of the solvent or water equal to 97.5 grams. The boiling point elevation delta T sub B can be determined using this formula. So delta TB is equal to I multiplied by K sub B and multiplied by small letter m, where I refers to the Van Hoff factor or index. All right, this is a measure of the uh, effects of solute on various colligative properties of solutions. Case of B is the molar boiling point elevation constant of the given solvent. And small letter m, of course, is the molarity or the molar concentration of the solution. All right? So, in this example, we first compute the number of moles of the solute, okay, which is 2.5 grams divided by 58.4 grams per mole. 58.4 grams per mole is the molar mass of sodium chloride. All right? So, when we do our math, we get this amount of mole of the solute, all right, equal to 0.043 moles in two significant figures. Next step is to compute the molality or the mole solute per kilogram solvent, all right, which is equal to 0.043 moles divided by 0.0975 kilogram. All right, so this is the mass of the solvent, all right, expressed in kilogram. So we will get the value of the molality equal to 0.44 molals. All right, small letter m is read as molals, which also means moles per kilogram. Right? Finally, we can now calculate for the boiling point elevation delta T sub B. Right? So that is equal to the Van Hoff index of sodium chloride, which is equal to 2, because sodium chloride is an ionic compound. All right, it can dissociate into two ions. All right, the positive sodium and the negative chloride ions. All right, so we multiply 2, all right, by the boiling point elevation constant of water, which is equal to 0.512 Celsius degree, or that can also be called Kelvin. And then that's per molal. All right. So we also multiply that by the molarity that we calculated here, 0.44 molals. And doing our math, okay, the computed delta T sub B will be equal to 0.45 Celsius degree or Kelvin in two significant figures. Hence, the boiling point of the solution will just be, all right, equal to 100.45 degrees Celsius. So this is the boiling point of the solution. And we also emphasize that this boiling point is at an atmospheric pressure equal to 1 atmosphere, or 1 raised to the 5th Pascal. That is the atmospheric pressure at sea level. Let's look at this second example. 20 grams of a non-volatile and non-dissociating solute is dissolved in 400 point grams. That means in 3 significant figures of benzene. The resulting solution boils at a temperature of 81.2 degrees Celsius. It's understood that the atmospheric pressure is 1 atmosphere. So the question is, find the molar mass of the solute. So we are given the mass of the solute, 20.0 grams, and also the mass of the solvent, 400 grams. This is the mass of benzene. Also, the molar boiling elevation constant, case of B of benzene, is given as 2.61 Celsius degree or Kelvin kilogram per mole, right? That is also the same as Celsius degree or Kelvin per molal, all right? And likewise, the boiling point of benzene is equal to 80.1 degrees Celsius. So our target variable is the molar mass of the solute. All right, the solute is not identified, but it is a non-dissociating solute, non-volatile and non-dissociating solute. All right, we are asked to find the molar mass of that solute. So we first compute the molality of the solution, small letter m. All right? Using the formula, molality equals delta T sub B divided by K sub B. All right? So, substituting, we have molality equals 81.2 degrees Celsius minus 80.1 degrees Celsius. That is the delta T sub B. And then divide it by the value of K sub B, or the molal boiling point elevation constant, right? Of the solvent equal to 2.61 Celsius degree or Kelvin kilogram per mole. So doing our math, we will get this molality, small letter m, equal to 0.421 moles per kilogram, or can also be called molars. So, getting the number of moles of the solute, all right, we just multiply the computed molality by the kilogram of the solvent. That is 0.421 moles per kilogram times 0.400 kilogram. And that is equal to 0.168 moles. All right, this is the number of moles of the solute. Lastly, computing the molar mass of the solute, we simply divide the given mass of the solute, which is 20.0 grams, all right, by the number of moles of the solute, all right, that we got here, which is 0.168 mole. So simplifying, we get the molar mass of the solute equal to 119 grams per mole in 3 significant figures. Our third example is about freezing point depression delta T sub F. This is another colligative property of solutions. So we have the problem. During winter, sodium chloride or calcium chloride is often sprinkled on icy roads to melt the ice and make driving safer. The solubilities of sodium chloride and calcium chloride are about 36 grams and 60 grams respectively per 100 grams of water at 0 degrees Celsius and at 1 atmosphere. All right. Question is, calculate the freezing points of both solutions to see which salt is more effective at melting ice. We first determine the molality of sodium chloride. That is, the percentage by mass, 36 grams per 100 grams, is multiplied here by the reciprocal of the molar mass of sodium chloride. That is, in 1 mole, there are 58.4 grams. All right? The unit grams cancels out, but there is 1 unit gram that has to be converted to kilogram. Right? So, the result is uh, the molarity equal to 6.2, and the unit is moles per kilogram, also known as molals. Similarly, for calcium chloride, its molality can also be determined, all right, by multiplying the percentage by mass, uh, 60 grams per 100 grams, okay, by the reciprocal of the molar mass of calcium chloride. That is, in 1 mole, there are 111 grams. And then, the unit of gram is converted to kilogram. All right? So the unit grams here cancels out, and we will get the molality of calcium chloride equal to 5.4 moles per kilogram, or 5.4 molals. All right? Next step in our computation, we compute the delta TF, or the freezing point depression of sodium chloride. That is, delta TF is just equal to I multiplied by K sub F and small letter m. All right? Substituting the given data, we have 2, all right, multiplied by 1.86 Celsius degree or Kelvin per mole times 6.2 molars. All right. So, the Van Hoff index, small letter I, of sodium chloride is equal to 2 because it has two ions when it dissociates in water. All right, the sodium positive ion and the negative chloride ion. So that's 2. And then the molal, all right, freezing point depression constant for water is equal to 1.86 Celsius degree or Kelvin per molal. And of course, the computed molality of sodium chloride, 6.2 molars. So doing our math, we will get the delta T sub F for sodium chloride equal to 23 Celsius degree. Right? And the freezing point, therefore, of the sodium chloride solution is just, or TF is just 0 degrees Celsius minus 23 Celsius degree, which is equal to negative 23 degrees Celsius. Likewise, we do the same procedure for calcium chloride. All right? So, using the same formula for determining the delta T sub F, all right? Take note, the Van Hoff index for calcium chloride is equal to 3, all right? Because when calcium chloride dissociates in water, there will be 3 ions, 1 calcium positive ion and 2 negative chloride ions. That's a total of 3. And then the same value of K sub F, all right? The molal freezing point depression constant of water is 1.86 Celsius degree per molal. All right? And then multiply it by the computed molality of calcium chloride, which is 5.4 molal. So, we will get the delta TF of calcium chloride equal to 30 Celsius degree or Kelvin. And that means, all right, the freezing point of calcium chloride solution is just equal to 0 degrees Celsius minus 30 Celsius degree, which is, of course, negative 30 degrees Celsius. All right? Hence, we say that the freezing point of calcium chloride is much lower than the freezing point of the sodium chloride solution. So, we therefore say that calcium chloride is more effective at melting ice. All right? It is more effective at lowering the freezing point of water because, as we have seen, its solutions contain 3 ions per formula unit. And in practice, calcium chloride is the salt that is usually sold for home use. All right, and it is also often used on highways. The third colligative property we'll discuss is osmotic pressure, denoted here by the symbol pi. All right, so osmotic pressure refers to the minimum pressure applied to a solution to prevent the inward flow of its pure solvent across a semi-permeable membrane. Its formula is pi equals the product of the Van Hoff index, small letter I, multiplied by the molarity, capital M, all right, times the constant, the universal gas constant, capital R, and the Kelvin temperature, capital T. So, once again, the number I, as we earlier defined, just for emphasis, it's the Van Hoff index or factor, all right? While the capital M refers to the molar concentration of the solute. Big R, of course, is the ideal gas constant, and capital T is the Kelvin temperature. Let's look at this problem. Okay, a 0.500 liter sample of an aqueous solution containing 10.0 grams of hemoglobin has an osmotic pressure of 6.0 torr at 25 degrees Celsius. What is the molar mass of hemoglobin? All right, so the molar mass of hemoglobin is our target variable. But before we can find that molar mass, we first convert this osmotic pressure 6.0 torr into its equivalent in atmosphere. So we just multiply that by the conversion factor. 1 atmosphere equals 760 torr. So the value of pi, or the osmotic pressure, is therefore equal to 7.9 times 10 to the negative 3 atmospheres. All right? And our next step would be to determine the molarity, capital M. All right? Which is just dividing the osmotic pressure by the product of the Van Hoff index, the universal gas constant, big R, and the Kelvin temperature T. All right, so we shall see this in just a while. So plugging the given quantities into the formula for determining the molarity, big M, we have 7.9 times 10 to the negative 3 atmosphere. Okay, this is the osmotic pressure. So that's to be divided by the product of uh, the number I, or the Van Hoff index, which incidentally is just equal to 1 because hemoglobin is a non-dissociating, non-electrolyte substance. So it's understood that the value of I is equal to 1. All right? The value of the big R, or the universal gas constant, all right, is 0.0821 in 3 significant figures. That's in liter atmosphere per mole Kelvin, or Celsius degree. And that's to be multiplied by the Kelvin temperature, all right, 298 Kelvin. So doing our math, we will get the molarity equal to 3.2 times 10 to the negative 4 molars, or moles per liter. All right? So, our next step is to determine the number of moles of hemoglobin. All right? So, we just multiply that molarity, which is 3.2 times 10 to the negative 4 moles per liter, by the given volume in liters, which is 0.500 liters. So simplifying, we get the number of moles of hemoglobin equal to 1.6 times 10 to the negative 4 moles in 2 significant figures. And finally, we can now determine the molar mass of hemoglobin. All right? So we just divide the given mass in grams, which is 10.0 grams, divided by the number of moles of hemoglobin, 1.6 times 10 to the negative 4 moles. All right? And simplifying, we get the molar mass of hemoglobin equal to 6.3 times 10 to the 4th power grams per mole. So that's it. We are done. Till the next episode, mabuhay, Masya Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.